Hi folks, Dr. Tom McNamara here again. Welcome back to our course in trigonometry. In this video we are going to talk about simplifying trig expressions. So we're going to continue our work dealing with the relationships satisfied by the trig functions, the algebraic relationships that the trig functions fit into, and we're going to talk about simplifying trig expressions. Just to give you some notes, some general principles here. First thing I would recommend if you want to simplify a trig expression is write all the functions involved using sine and cosine exclusively. If you go back and look at some previous videos, you'll find information about the reciprocal identities. So secant and cosecant can be expressed in terms of sine and cosine. You'll look at the ratio identities, so tangent can be expressed in terms of sine and cosine. So if you're looking to simplify a trig expression, write everything in terms of sine and cosine, and then start doing algebra, try to cancel, etc., etc. Let's look at a couple of examples. I've got some right here. Okay. So simplify this expression here. Let's say we've got tan theta times cosecant theta. Okay, so tan theta times cosecant theta. Well, using our ratio identity, the tangent function, we can rewrite that as sine theta over cosine theta. Cosecant, using the reciprocal identity, that's 1 over sine theta. Here the sines cancel each other out. So that's equal to 1 over cosine theta. 1 over cosine theta we know is secant theta. So this expression right up here, tan theta times cosecant, is actually equal to secant. Okay, so that's what I mean by simplifying trig expressions. Let's do a couple more. Okay, let's try this one. Okay, we'll do that. Sine theta plus 1 over cosine theta. Or, in fact, maybe we'll start out like this. We'll say sine theta plus secant theta. All right, so following our principle of writing all the expressions, writing all the parts of the expression using sine and cosine exclusively, we start with this, we rewrite and get this. We replace secant with 1 over cosine. Okay, now we're adding fractions, okay? And of course, to add fractions, we need a common denominator. So we can't express this as a fraction. You can put anything as a fraction, right? Think back to your algebra or your arithmetic. The number 4 you can view as a fraction, 4 over 1. So this expression we can view as a fraction. Just put a 1 in the denominator. Now, we can't combine these just yet because they don't have a common denominator. So, I guess we'll have to use cosine as our common denominator. If you're stuck, always multiply the denominators that you have and you got your common denominator. Okay, so I'm going to hit this top and bottom with a cosine. Sine theta times cosine theta over cosine theta. Plus 1 over cosine theta. And now that we've got a common denominator, we can combine these into one fraction over that common denominator. Right. So this is the combined expression of those two. So once again, following that principle of writing everything in terms of sine and cosine exclusively, and if you ever have an expression with fractions and you got to add fractions, well, get yourself a common denominator and then add fractions. I want to do a couple of examples that involve the Pythagorean identities. You'll remember those from a previous video. So first one was like this: sine squared theta plus cosine squared theta equals 1. Leave me some space here. I'm going to put a couple different versions. Another variety of this Pythagorean identity is down here: tan squared theta plus 1 equals secant squared. And a third one is 1 plus cotangent squared is cosecant squared theta. Okay, this is kind of the most basic one because we can derive these other two from this one. But some alternatives to this are, like if I ever see 1 minus sine squared theta, that is equal to cosine squared theta. In other words, if I just take this, if I want cosine squared theta by itself, I would subtract sine squared from both sides. So this is saying if I ever see an expression that has 1 minus sine squared theta, I can replace it with cosine squared theta. Similar reasoning, if I ever see 1 minus cosine squared theta, I can replace that with sine squared theta. And likewise, if I ever see this, I can change it to secant squared. If I ever see 1 plus cotangent squared, I can replace that with cosecant squared. Okay, let's do a quick little application. Simplify square root of 16 minus x squared by replacing x with 4 cosine theta. Okay, so in this example, we're going to make use of one of our trig identities. So if I replace x with 4 cosine theta, my expression turns into this. Okay, so instead of 16 minus x squared, I got 16 minus 4 cosine theta squared. Now, parentheses are kind of important here. I'm taking 4 cosine theta times itself. 4 cosine theta times 4 cosine theta. The two factors of 4 multiplied together give me a 16. 16 cosine squared theta. Notice both terms have a 16. Going to factor that out. Now look what I have right here. 1 minus cosine squared. Whoops. I guess it's this one down here that I want to use. 1 minus cosine squared, we can replace that with sine squared. 16 sine squared theta. And now we're going to use some facts about properties of square roots. Okay, remember we talked a lot about square roots early on in this course. Square root of a product is the product of the square roots. I can take the square root of 16, which is 4, and the square root of sine squared. Well, square root and a square, those undo each other. They're inverse operations. So I'm left with sine theta. Okay, so a couple of examples of using the identities that we've discussed earlier to simplify trig functions. So the basic principles involved are, number one, if you got a trig expression, rewrite everything in terms of sine and cosine exclusively. And then try to do some algebra. Look to cancel stuff from numerator and denominator if you got multiplication. If you're adding fractions, get yourself a common denominator before you proceed. Another principle involved is if you see squares, if one of the trig functions is squared, look to bring in your Pythagorean identities, and that can help you simplify your expression.